We were discussing Poisson's equation last time, and we had got it all set up, talked about the two different types of boundary conditions. Dirichlet, where you fix a value at the end and you get funky stuff like that, and von Neumann boundary conditions, where you set the electric field to 0 and you end up with very smooth potential with 0 electric field at the end, because that's what your boundary condition is enforcing. And we showed how to, for Dirichlet, you modify the vector on the right-hand side of this equation, and for von Neumann, you modify the matrix, the corner elements of the matrix itself. So for the Dirichlet boundary conditions, we added these extra terms over on the right-hand side, and for the von Neumann ones, we just added this term, epsilon 1/2, onto that corner term, and we did the same thing for the lower corner term. That took care of the boundary conditions. And now what we're going to talk about is, so you've got these two equations now. You can think of it as Schrodinger's equation or your negative equation, where you're calculating the charge quantum mechanically, the electron density and hole density that goes into that row. And then you're solving this to get the phi, and that goes back into your Hamiltonian to get a new row. And so the question is, how do you go about solving these in some way to get them to converge as quickly as possible, right? I mean, do you just like substitute the phi back into the Hamiltonian, get a new row, and just go back and forth, or do you do something more smartly than that? So that's what we're going to talk about this time. We're going to talk about convergence algorithms, and particularly the one we're going to focus on is the Newton-Raphson algorithm, because that's always worked pretty well. It seems to give the fastest convergence that we've found. There's one that seems a little more robust but a little slower. I'll talk about that at the end. So the general form of the equation, sort of write it symbolically, that we're solving is this, right? And we've discretized it. So this, by writing it between the brackets, what I really mean is the matrix, that discretized matrix we were just looking at. So that discretized matrix that was multiplying phi, that's what I mean by the thing in the brackets. And so that's multiplying the vector phi, right? So one value of phi for each site in your discretized device, right? One phi for each site. And that's going to equal your vector rho, or your array rho, however you like to think about it, or one value of rho for each site, right? So that's sort of what we're solving. I guess it's negative rho, actually. Negative rho. And this rho is really a function of phi. Your rho is really a function of the vector. So this rho is really a function of phi. And so this is a nonlinear, because, rho is sort of a nonlinear function of phi. When you think of, we're getting it out of, by solving the Hamiltonian, if you think of Schrodinger's equation, taking the magnitude of the wave function squared, summing them up, weighting by the Fermi factor, it's a very nonlinear function of phi, right? And so overall, this is a very nonlinear equation because of that rho dependence on phi. And so what we're going to do is define a new function. And so this is the way, we're just setting this up the way the Newton-Raphson algorithm is always set up. We're defining a new function, and so by a vector, I just mean one, what I mean by a vector are these things. So rho in this notation is my vector row. In terms of MATLAB, it would be an array, right? One value for each site. So I'm defining this new vector or array, capital F, which is simply taking these two terms above, moving them both on the left-hand side so that the whole thing is equal to 0. Okay, so all I've done is move both terms over onto the same side so the whole thing's equal to 0. I call that F, uppercase F. So, I mean, this is the way Newton-Raphson is always set up. So the equation for the starting point of the Newton-Raphson scheme looks pretty simple. That's what my equation is. That's what my equation is when you have the solution. Right? When you have your final solution, this is true. When everything's converged, this is by definition true. Right? So this is what you're trying to obtain. You're trying to obtain the solution where this uppercase F equals 0. And so the Newton-Raphson scheme goes like this. You're trying to, at each step, move in the direction towards this solution. And so you assume that you're close to that you're near the correct solution for phi. And so then you write F as a first order Taylor series expansion around small change in phi. So in terms of indices, Fj, which is a function of all phi, plus sum over I, dfj, d phi I, delta phi I. So I just wrote it out as a first order linear Taylor series expansion around a small change in phi, assuming that you're close to the solution. And so now you just move the leftmost term over to the right hand side, and you've got sum over I, dfj, d phi I, delta phi I is negative F, Fj. And now I'm going to add indices in terms of iteration number. So if I'm at iteration m, this would be from iteration m, and this would be the new solution from these old values for f. This is my new solution. M plus 1 would be the new delta phi to go into the next iteration. So I'm getting a new estimate for the change in phi. This is not the new phi, this is the change in phi from the old phi. So I have to add this to the old phi to get my new guess. And so now let's see what that means in terms of, we have to now, figure out what to do with that derivative there, that df, d phi term. Because it, this looks like a matrix equation. You got a j and an I, delta I, so it looks like some kind of matrix vector multiplication. But this matrix is different from the one we started with. So there's two terms. If we go back and look at what our definition for F, we define two parts to it, F1 and F2. So here's F1. Call this F1. Here's F2. And then we'll have to take the derivative, figure out how to take the derivative of each term. Did you see that? My two right? The two pieces to F, right? Call F1 and F2, and now we got to take that derivative, df, d phi. We got to take them each independently. So, well, first we'll do F1. So that's actually the easy one. df1 comma I d phi j is going to equal dd phi j sum p, this matrix, which is just a bunch of constants that never, right? This matrix is only a function of the type of materials you're having. It's all the epsilons and the geometry, which determines how they're a function of position. So this matrix is just a matrix of constants, so it's not going to be affected by the derivative. And it was just a bunch of epsilons and constants in that matrix, phi p. So the only thing that's getting hit by that derivative is the phi sub p out there. So this is, I need my indices here, so I comma p. So that's the matrix, the indices for the matrix there, times phi p. So sum over p, that's just that matrix vector multiplication. So the I comma p are the indices of the matrix, and then times phi sub p, sum over all p. So you're just normal matrix vector multiplication. And so the only thing, all I'm getting is that, this, so I get sum p, this matrix, which is a bunch of constants, I comma p, times d phi p, d phi j, and this thing is just delta p comma j. You just think of those as all independent variables, the phi's, and so you only get one when p equals j. And so that kills off the sum, and so this is just equal to my matrix. So that's easy. df1 is just that matrix. df1 comma I d phi j is just the matrix ddz, epsilon ddz, that discretized matrix I comma j. That was the easy one. We already had that term. And since that term is just linear in the phi, this kind of makes sense. Just you know, taking the derivative like a constant times phi, you just get the constant. Happens to be a matrix, but in terms of phi, it's a constant. Okay. Okay, so we got one term. Now we got to work on that other term, which is not so straightforward. So the other term was f2 was equal to this vector rho. And we got to take the derivative of that with respect to phi. And as we said, this is a highly nonlinear function of phi that comes out of, solving the negative equations and all that. So we got to figure out how to go about taking this derivative. And the key here is that, if we go back and look at our starting point, I guess this, or yeah, this, right? This, what we wrote down here. I mean, we're starting with sort of an approximate, right? First order Taylor series approximation for the new delta phi. Right? This is an approximation to begin with. And all we're looking for is solutions of delta phi that are sending us in the right direction, towards the solution. So we're starting with an approximate equation, and so this thing, this whole thing is termed your Jacobian. And all you need is a Jacobian that's going to point you in the right direction. You don't need the exact Jacobian. I mean, so this term is exact, the one we first from F1, because it's just linear in phi, so that's exact. For the second term, we just need a good approximation that's going to point us towards the solution. So let's go back and look at what is rho. So rho was equal to q times nd plus minus na minus minus I guess plus p minus n. And we said that the way we're doing things, these are just constants, they're not functions of phi. They're just determined by whatever your doping density was. So if I take the derivative, they're just going to disappear. And so all I need is the derivatives of p and n with respect to phi. So I'm going to need negative q d ni d phi j and q d pi d phi j. That's what I'm going to need, or some approximation to those. And then if you recall, in terms of our generalized boundary conditions, we had these two different regions, what we call the true non-equilibrium region and then these band-bending regions. So I'm going to need values in these equilibrium regions, but where there's still a non-zero electric field, and then in the non-equilibrium region. And the way we're going, so there's a little slight differences in the expressions we have to deal with in those two regions. So first, let's look in the equilibrium regions. So in the equilibrium region, I have dnj d phi I is equal to, assume I have infinite cross-section and x and y, so I'd be integrating over a two-dimensional k, d phi I times my Fermi factor. Okay, so the only thing that's affected in this equation by phi I is the spectral function, because phi goes into the Hamiltonian, and the spectral function comes out of the Green function, which comes out of the Hamiltonian, through the E minus hg equals I. So the only thing that has a phi buried in it is the spectral function. And you actually can do that functional derivative. It's not what we want to do or what we're going to do, but just for your sort of cultural awareness, let me show you how that's done. So we have A, so this is not how we do it. Just to be clear. But it's interesting to just show how this works. So we have A is negative 2 imaginary g. And so, to take dd phi of A, I need to take dd phi of G. Right? Same thing. So let's look at dd phi of G. So G inverse is equal to E minus H0 minus U minus sigma. That's G inverse, and this U is negative Q phi. Right, that's the potential that I'm putting in there separately so we can see where it is. And so I want to take, I need to take something like dg du. And if I can do that, then I can, that's within a constant of dg d phi, right? Because u equals negative q phi. And so I use the fact that dg inverse du is just equal to negative I, because if you look back, there's G inverse at the bottom, right? The U only shows up linearly, so that's clearly true. And if you think of these as, you know, functions of R, then, or functions of position, that's all matrices, and instead of -1, you get negative identity matrix. And I can explicitly, you know, do this, and that's got to be equal to just taking the derivative of G inverse. That's equal to negative G -2, just like you would take a derivative, times dg du, explicitly taking that functional derivative. And just the way you'd normally take a derivative, right? The derivative of G inverse you'd say would be negative G inverse G to the -2, right? Times dg du. And so we just use this and multiply through by, you know, G negative or G squared, and you get that dg du is equal to G squared. And so that's all nice and formalism, and you'll see this sort of thing in Kadanoff and Bain for other purposes, but this is not what we want to do, because if you were going to use this for your Jacobian and put this back in this expression for the charge density, if we were going to replace, you know, AJJ by G squared, it means we have to calculate the entire G to calculate G squared, and we've taken great pains to avoid calculating the full green function by, you know, developing this recursive green function algorithm. So we only needed to calculate the diagonal elements in first block column, because if you need all the elements, it means you just have to just go ahead and invert the entire matrix E minus H, and we wanted to avoid that at all costs. So this is absolutely not what we want to do. We're going to do something much simpler that also works really well. So we need to go back and to develop this very simple approximation that we're going to use. We need to think of what happens when you change the potential. You know, when you have a change in potential locally, what's happening? Well, in the equilibrium region, you have your conduction band edge, say for electrons, and you have your Fermi level, and a change in delta U, let me see, am I doing? A change in delta U just will shift your conduction band edge just by, you know, to some new value, EC plus delta U. Right? That's what a local delta U does. And so in the simplest picture, your local density of states just gets shifted up by this energy delta U. So if I have, you know, my energy grid, and I have calculated my spectral function, which is in that integrand, right? In this integrand here that we needed to integrate over. So I have my spectral function. And now if I shift my band edge up, it means that this thing goes to A at the same energy. I'm just evaluating, it's like evaluating the spectral function at shifting, I'm just shifting rigidly the value of the spectral function. And so this value would be used in that integral on the previous page, locally, at every point in that simple picture. But of course I'm going to get the same integral if instead of shifting the conduction band edge, I just lower the Fermi level locally. Right? So I could also, I get exactly the same thing as instead of doing that, I lower my Fermi level locally and don't shift my spectral function. And because I have, it's just, you know, I'm multiplying the two things together, I'm going to get exactly the same answer. Whether I lower the Fermi level or raise the spectral function doesn't matter. I can do one or the other. And so this is how we get this simple approximation that we finally use for this functional derivative. So if I just ignore that integral over k to keep the equation somewhat simple. So now I'm looking at integral dE over 2 pi dd phi j a j j e f of e minus mu. So I'm looking at this integral, and what can I say? So that's equal to du d phi, and this just gives me my value of, I guess, negative q out front. The integral dE over 2 pi d du, and so this would give me my negative q, just going from energy to potential. And if you look at the way that that delta mu entered in here, it enters just like energy but with a negative sign. So this is equal to q integral dE over 2 pi ddE of a of e f of e minus mu. So by switching from ddu to dde, I pick up a negative sign, which cancels the negative sign out front. And now I integrate by parts, and so that's equal to q integral dE over 2 pi dde of the whole thing minus integral dE over 2 pi a of e dde f of e minus mu. And so the final, what we finally use is that d n I d phi j is equal to negative q integral dE over 2 pi a I of e, put a plus sign there, and then negative dde f of e minus mu delta I comma j. Okay, so one approximation is that, you know, at a given site, you're approximating this derivative as diagonal, so you're not worried about like dni d phi j. And all you're doing is from this perspective we talked about earlier, you're just, instead of shifting the potential, you're shifting the Fermi level locally, because we're talking about the equilibrium regions of the leads. And so so this is for the equilibrium regions of the leads. Okay, this would be the form of the Jacobian used in the equilibrium regions. And I guess if we go back to the equation we first wrote down, writing out all the gory parts, we have we had an integral over k and all that. That would be the whole thing. And for the, the right side, you just replace for the right side. Mu left just is replaced with mu right in this expression. In the right equilibrium region. Okay, so that would be the Jacobian in the equilibrium regions. Now what about in the device region? Okay, so in the device region, or non-equilibrium region. So we start with our non-equilibrium expression for the electron density, Nj, which is 2 over A. And if we go through the same steps as before, you basically end up with the same result, that you just take the derivative of these Fermi factors, negative derivative of the Fermi factors with respect to energy, and that's the approximation you use for your Jacobian in the non-equilibrium region. So dnj d phi I in the non-equilibrium region. So it looks, you end up doing the same thing for the non-equilibrium expression as you do for the equilibrium one, if you work through it. And so this is the Jacobian that we use. And we had a more numerically efficient form for the electron density that looked like, I think you had an A left, something like an A left times, well, I think it was like just F left minus F right, right? Plus maybe the full spectral function times F right, something like that, or F left. And so if you use this other more numerically efficient expression, everything just all these get replaced with just negative df dE. So dfl dE, negative dfr dE, and negative df. So wherever you see an f, you replace it with negative df dE in the calculation of your charge for your Jacobian. Okay, we talked about electrons, so you may also have holes in the problem, in which case you need dp d phi. But for holes, you use your negative expressions for holes are exactly the same as those for electrons, except wherever you see an f, it gets replaced by a 1 minus f, right, in all those integrals. So the expressions are all the same, but wherever you see an f, it gets replaced by 1 minus f when we do the integrals. And therefore, everything goes through as before. It means that dp d phi, the change in the whole density with respect to this potential, is just negative change in the electron density with respect to phi, which makes sense, if you're getting less holes, you're getting more electrons, or vice versa. But since, the charges have opposite signs also, so, rho sub p is qp, and rho sub n is negative qn. So there's two negative signs involved which cancel. So therefore, the Jacobian d rho I d phi j is the same for electrons and holes, which is nice. It's exact. So what we wrote down is the Jacobian for both electrons and holes. Okay, so we've got we've got the Jacobian. Once we have this Jacobian, this is the matrix vector equation that we solve at each iteration step to get the new the new change in phi. We'll talk about what to do with that in a second. But before we talk about that, I want to say something about the limits of integration, which we haven't discussed before, I don't think. So it comes about when you have both electrons and holes in the problem. Now, if you go back and look at this, like this expression over integration over energy, I didn't write any limits. So if you have, you're going to have a band gap of some finite, and stuff in the valence band you should probably consider to be in our usual electron hole picture that we use a hole, and the stuff in the conduction band you want to think of as an electron, and so you have to sort that out and associate holes with holes and electrons with electrons. And the way you do that is by defining the limits of that integration. So in a full band model, which is where this becomes sort of tricky, so in a full band model, ahead of time sort of the unperturbed energies of your conduction band edge and your valence band edge. Right? You could just do an EK, for example, and know what those energies are that pop out of the full band model. Okay? So the band edges ahead of time. Say you'd get them from your EK calculation. And then the band gap, of course, and that'd just be the difference. So all that going into the calculation. And then in the device, the band edges start being locally become a function of position, because you have this position-dependent potential everywhere. So your band edges are going to now become a function of position for site J. There'll be whatever there is with no potential minus Q phi sub J. And same thing with the valence band edge. And so if we think about what's happening, you're going to have these regions where there's a lot of band bending. And under high electric fields, you can, if the fields are high enough, you can have things like Zener tunneling, like in a tunnel FET, for example, where you're tunneling from the valence band to conduction band. And it gets a little bit fuzzy on what to consider an electron and what to consider holes, because, you have this, electrons are moving from the valence band into the conduction band. And so, for that to happen, in the extreme case, when you have a very high electric field here, there can be a lot of states in what you would consider to be the band gap, because they're tunneling into it. Right? The states are tunneling into the band gap, and it's no longer clear that you can just integrate right to a band edge. And so the algorithm that we developed, and all this sort of thing is just something you figure out by trial and error, is that everywhere locally you define the middle of the band gap. So you got this you're keeping track of the potential, so your valence band edge, your conduction band edge, and you take the halfway point, and that's your middle of the band gap. We can call that E sub I, right, like you do in your semiconductor books. They call that in the intrinsic level. It's not exactly the intrinsic level. We'll just call it that. It's the middle of the gap. And so when you do these integrals over energy, for holes, you integrate, from this energy down, and you call that anything you pick up there as a whole. You do that, weight that by 1 minus f, and for electrons, you integrate upwards, and you weight that integral by f, and whatever you pick up there is an electron, and that's the way we sorted it out. And so, even in the regions where there's band bending, since there's a local calculation for each site, you're doing the same thing. So, as a function of position, the limits of your energy integral are constantly changing as a function of position as you calculate electron and hole density throughout the device. So the limits of that integral for your electron and hole density are now become a function of position as you move through the device. And so to calculate F, that term on the right-hand side, we had our sort of Newton-Raphson equation was it was like, df d phi delta phi is equal to negative f, right? That was the equation we were solving. And so in negative f was just the thing we started from, right? F was this matrix times phi plus rho. And so to do, this is the equation I have to solve over here on the left. And to set this up, I need two things. I need the value of rho, and I need d rho d phi. D rho d phi. Right? I need rho to get f. I need d rho d phi to get df d phi. So I need those two things at each iteration to finally then solve this matrix equation to get the new delta phi. But, if you look, the equation for n and p and the equation for dn d phi and dp d phi were almost the same equation, except I just replaced f by negative df de. If I go back and look at this, all these equations, all I do to get dn d phi is everywhere where I saw an f, I replace it with negative df de. It's almost the same equation. So what that means is that, you can, in the same loop, when you're doing this, you can simultaneously be calculating n and dn d phi and p and dp d phi. And it's really just like no extra work at all. You multiply a by f, or you multiply it by df de. And furthermore, if you make use of the fact that this is a very nice relationship, you should all remember. Negative df de, negative df de, which is what you need when you're calculating dn d phi or dp d phi, is just equal to 1 over kt times f times 1 minus f. And so, if you're doing this integral, you've already evaluated f to get n and p. And so you have the value for f already, and you just multiply times 1 minus f divided by kt, and you get negative df de. So it's almost like no work whatsoever to do this extra calculation to get dn d phi and dp d phi, which goes into that Jacobian. This is a really nice thing to remember. You've set this all up, you've calculated everything you need, and then you go ahead, and this is what's in red here is now just a normal matrix vector equation that you send off and solve for delta phi. It's in our 1D chain model, it's a tridiagonal matrix, right? It's the simplest sort of matrix vector equation you can have. You get delta phi, and then what? So, what comes out of this is your delta phi that you're going to use. That's not, sorry. Delta phi. That's a bam. Delta phi, it's a m plus 1 that you're going to use in the next iteration of when you update your Hamiltonian. And so what you do with that is you have to update phi. So phi m plus 1 is equal to your old phi from your last iteration. Plus, you don't just add it on, you have some factor out front I'll call alpha, delta phi, m plus 1. And this alpha, we just call it a convergence factor. For us, it's usually something that's lying between 0 and 1. If everything is really robust, you can make it greater than 1. Up to maybe 2, but usually for everything we do it's something less than 1, and often a lot less than 1, like 0.1 or 0.05 or something like that, depending on how things are converging. So the value is going to depend on how well the equations are converging, and usually, the harder it is to converge, the smaller the value you're using to make very small little corrections at each step. If it's too large, you can get into a situation where you're just kind of oscillating and your delta phi is going positive, negative, and you're not really going anywhere. And finally, for convergence, like, when are you done? Well, you're done when delta phi gets really small in some sense, right? So you're converged, and so when you're getting delta phi is in some sense small, then you're done. It means there's no more corrections to be made to phi. And so what do we mean by small? Well, since this is a physics problem, we do have some idea of what we mean by small. So for example, if the change in phi is, say, on the order of or smaller than 1 microvolt, then you're definitely, who cares about a change of a microvolt, right? And often we may use something even, if delta phi is less than or equal, say, even 0.1 millivolt, call it done. Depends, just how things look. But physically, that a tenth of a millivolt doesn't matter. I'm thinking about room temperature. Tenths of a millivolt doesn't matter.
Is it relative change of delta phi or just the value of delta phi?
Say that again?
I mean the delta phi, it's the relative value of change.
That would be at every position.
Every position.
That's usually the way we do it. We're using like, okay, so this would be like, the way we usually set it up, this would be like delta phi I magnitude max would be less than those values. You just keep a running, maximum value, and if all the delta phi's at each point are less than that, then call it good. And so, I've always liked whenever you can, make use of absolute values, because, sometimes people do like some kind of ratio test, so it's like, delta phi new minus delta phi old over something, delta phi old or something. And they look at something like that, like some percentage change. But, that percentage can be huge, and yet the absolute values can be totally irrelevant.
I mean, if I can convert it with this condition, then of course the upper condition will be true, right?
Yes, but the upper condition can be true, and this lower condition may never be true.
Yeah, sure.
Because, if this is like 1 e to the minus 10th minus 1, e to the, 2e to the minus 10th over 2e to the minus 10th. That's 100% change, right?
Yeah.
But it doesn't matter. Because we're doing physics problems, usually you can define something physical and use an absolute convergence criteria. And I always prefer that because usually you'll find, we would always, the Poisson solution is, because it's a self-consistent solution, any self-consistent solution can be kind of tricky. And you'd find like some nodes that just kind of just keep going up and down and up and down. Having this kind of thing, like nobody cares. It's something really small, but it's like 100% fluctuation every time. So, and yet it's 100% of something that's negligible. So, when you can, it's much better to look at some absolute convergence criteria. So this is Newton-Raphson. This is how it works. This is the algorithm. This is how we calculate the Jacobian. And it's just been like the real workhorse of our NEGF-Poisson solvers. And it's the fastest one we have, the fastest scheme. But there is one that seems to be slightly more robust, and that is the Broyden-Anderson scheme. So that's sort of the end of Newton-Raphson. Another one, Broyden-Anderson, and we actually sort of discovered this when we were working with the Fireball code, and it's actually what is built into the Fireball code. And I think it's used in other DFT codes. So Newton-Raphson for us is the fastest, but it's slightly less robust than this Broyden-Anderson scheme. So what we did in some codes was we set it up to do Newton-Raphson, and if it didn't converge, then we'd switch over to Broyden-Anderson and see if that worked. And sometimes it would, sometimes it wouldn't. Broyden-Anderson is, that would take a whole nother lecture. We're not going to go into that. It's probably one of the best starting points is the appendix in Martin's book on density functional theory. And he gives the original references where it was developed. I think it's you'll find it in Chirole's code. Okay, so those are the convergence schemes. Now, given all that, there's still some funny things that can happen even after you've converged that are good to understand. And you'll see this, what I'm going to talk about, all throughout the literature and a lot of published results. All right, so maybe I can just pull up a picture without trying to draw this. I'll just draw it. Okay, so if you're modeling a FET, there's been a lot of use of NEGF-Poisson to model FETs in recent years. In the off state, your conduction band profile would look like this. You'd have a big barrier separating your source and your drain. And say your Fermi levels like this. Mu drain, mu source, and your conduction band edge. That'd be your potential profile going from source to drain of your FET in the off state. And then you start applying a gate bias. Your source and drain bias are fixed, so nothing is happening. So that means your Fermi levels in the source and drain are fixed. They're never going to move, okay? And we're using our von Neumann boundary conditions so that this is our reference energy of 0. Mu s is our reference energy of 0 in the source. So von Neumann boundary conditions. And so we start applying a gate bias and start pushing this barrier down. Gate bias. And then everything looks reasonable until the barrier starts getting to be sort of on the order of the source Fermi level. And then something funny happens. So when we get the barrier down on the order of the source Fermi level, like this, so it's turned on nice and hard, you see something funny happen over here. The conduction band in the source falls. And remember, the Fermi level is always fixed at 0. And on a very fine scale, you will see that the conduction band out here rises a little bit simultaneously. Again, mu d is fixed as just mu s minus q vdd. So the source conduction band falls as the gate barrier, or channel barrier, as a channel barrier. I really should say channel. It's a channel barrier. Okay, so that source conduction band edge starts to fall. And this is, so I'm not, and this happens when I'm using this whole region, I'm not using any of those generalized boundary conditions, so the entire region is non-equilibrium right out to the ends. So I'm calculating the charge using the non-equilibrium expression throughout the entire region. Okay, there's none of these equilibrium regions here. I'm using the non-equilibrium charge expressions everywhere. So the question is, why is the conduction band in the source falling? And right away, let me say this is what they call a spurious result, meaning it's an artifact of the algorithms and the calculation. So we need to understand what's happening and why this happens. So what do you think? And if you, again, if you look through the literature, you'll find this effect in so many calculations, and no one has ever spoken about it in the literature or in any book ever, anywhere. Okay, so what do you think is happening here? Why does that source conduction band start falling when this device starts getting turned on really hard? Any ideas? Let's think about what's happening. It's really, yeah, you really can't think physically. You really have to think in terms of the algorithms that are being solved to do this. So first thing to keep in mind is that mu s is fixed. Your conduction band edge has fallen. So it looks like you would think that the charge density must be increasing. And yet you know Poisson's equation is giving you a solution of charge neutrality in the leads. Poisson's solution is enforcing charge neutrality in the leads, so the charge is not increasing, and yet the conduction band is falling. How can that be? Seems like a contradiction. So in all cases, you know, back here, N is remaining at your doping density in the source. So to understand what happens, we need to go back and look at the equations that we use to get the charge density here. So the non-equilibrium charge density, all right, so that's the expression for the non-equilibrium charge density. And, you know, for any normal FET in this difference here, QVDD is at least like 0.4 volts or more. Even 0.3 volts, doesn't matter. At any rate, it's always on the order of like at least 10 kT, right? At least greater than or at least 10 kT. Which means that at the energies of interest in the source, this guy over here is essentially 0. at the energies of interest in the source. So we're calculating, this is 0 in the source, right? So at the energies of interest in the source, where we're calculating, doing this integral in the source, that Fermi factor, the value of that Fermi factor up at those energies is 0. Because you're more than 10 kT above mu sub d, right? So what I'm calculating in the source then is just that nj is 2 over a integral. So that's what, if I'm using this non-equilibrium expression, what I'm calculating in the source. Because I'm weighting the right injected spectral function by 0. Okay, so that's what we're actually calculating to get the charge density in the source. Now the next thing to note is that the total spectral function A is the sum of the left and the right injected spectral functions. And if you have a big barrier separating the two regions, this wave coming in here is pretty much entirely reflected. And this wave coming in here is entirely reflected. And so in this region, so in the source, A left equals A, at least in the off state, when that barrier is there. And so when that's true, then it looks like, this expression here is just your usual, if I just replace A left by the full spectral function, that's just your usual equilibrium expression for the electron density, which is what you would expect. Right? If I just means that in the off state, when I have that big barrier there, then it's A left is essentially the total spectral function in the source. And so that expression in red just reduces to the usual equilibrium expression for the charge density. However, in the on state, that barrier is no longer there. My Fermi level is up here. I've got something like that. If we just assume, just for the sake of argument, perfect transmission above the barrier, perfect transmission above the barrier, nice smooth barrier, no reflection. All right. Then above the barrier, I have that A equals. So what that would mean is that above the barrier, A left is equal to A right. If there's no reflection, I'm just having more or less equal flux. A is the sum of the two. The total spectral function is the sum of the two, which is just to say approximately 2A left, which means that now in the on state, A left is just A over 2. And so suddenly it looks like my density of states has been cut in half above the barrier. So A left is reduced in the source because none of it's being reflected. Okay, so A left is being reduced. It was all being reflected. Now it's all being transmitted. So it's cut down by a factor of 2. It's compensated by the fact that A right, is coming in, but we're weighting A right by 0 because of that Fermi factor in the right. A right is weighted by 0. And so the only way to preserve charge neutrality once this happens is to lower the conduction band edge, because it looks like your density of states is being reduced. And that's exactly what Poisson's equation does. It's trying to preserve charge neutrality, so it lowers the conduction band edge until it gets charge neutrality. Now, physically, it doesn't really seem reasonable that way over here, the conduction band edge should be affected by what's going on in the barrier region. I mean, somewhere like several screening lengths or scattering lengths back from the channel. It seems like physically phi should not depend on what's going on in the channel. It should not depend on either the channel or the value of mu in the drain. Physically, if you go back a couple of scattering lengths or a couple of screening lengths, it should be a fairly local function and not depend on what's going on up there. And so, to implement that physics, we use our generalized boundary conditions that we described before, where in this region, somewhere back here, we just use the equilibrium expressions to get the charge density, or we just use the exact spectral function instead of A left. And then this doesn't occur, because the spectral function isn't affected. The full spectral function is not affected by much at all by what's going on in the barrier. Okay, so to avoid this, we use these generalized boundary conditions that we talked about in the last lecture. So the one final homework problem is just, there's only one problem for this chapter 5 homework. And it's a very easy problem. You just go through what we just did, and you explain why over on the drain side, just using the negative equations like what we just did, at the same time that this is going on in the source, that this is dropping down, this is coming up a little bit. Explain why that's happening. So it's chapter 5. There's only one problem there in chapter 5. And that's the last, that completes the homework for the course. Okay, I guess it's time to take a break.